Ready to run blazing fast, state-of-the-art AI vision on a standard CPU without a single drop of Python? Today, we're unlocking the ultimate C++ pipeline for object detection, pose estimation, and segmentation.
This video is curated by Dr. Satya Malik and created using AI.
Let's dive right into this. First, we'll set up the C++ computer vision engine. Second, we establish our real-time detection baseline. Third, we level up to pose estimation. Fourth, we hit the boss level with instant segmentation. And finally, we'll cover benchmarks and gotchas.
Section 1. The C++ Computer Vision Engine.
Moving away from the cozy, pre-built environments of Python into the raw power of C++ can feel like a huge leap, but it is absolutely essential and honestly incredibly rewarding for real-world edge deployment. On the Python side, you're usually lugging around these massive, heavy dependencies like PyTorch. Now, PyTorch is fantastic for training your models in the cloud or on giant GPU rigs for sure, but it is incredibly bloated for edge devices, mobile processors, or just standard desktop applications. We want to run fast and lean. By exporting our trained YOLO26 model to plain ONX files, which is basically just an open standard format for representing machine learning models, we can drop the Python environment entirely. This lets us tap into a completely self-contained, highly optimized, and incredibly lightweight OpenCV5 runtime natively in C++.
Before we go further, this video is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai. Okay, so setting this up requires building OpenCV5 directly from source. There's no simple plug-and-play package installer shortcut here when you want the bleeding-edge features. It takes a few extra minutes, but it gives you total control. First, make sure you're building directly from the 5.0.0 branch so you get the latest graph engine updates. Second, you absolutely must enable FFmpeg during your build by setting with FFmpeg to on. If you skip this, your video processing simply won't work and you won't be able to read or write video files. Finally, we actually intentionally turn with CUDA to off. Now, why would we turn off GPU acceleration? Because our primary goal today is to prove just how beautifully and efficiently this entire pipeline runs on pure CPU power alone.
Section 2. Real-time object detection baseline. The architecture of YOLO26 is just beautifully simple. It operates as an NMS-free end-to-end detector. Now, NMS, or non-maximum suppression, is typically this rather messy post-processing step used in older object detection models to filter out all the overlapping duplicate bounding boxes that constantly get drawn around a single object. But YOLO26 deduplicates its own predictions internally, right inside the neural network. It exports to our ONX format as a single fixed tensor of shape 1 by 300 by 6. And because you entirely bypass that complex NMS filtering code, all you need on the C++ side is a basic score threshold to weed out low-confidence guesses and a simple coordinate rescale to match your image size. Your C++ deployment code stays incredibly minimal and clean. In the real world, this minimal C++ pipeline is remarkably robust. When analyzing heavily out-of-focus, blurred stadium footage, the system gracefully handles the visual noise. It cleanly drops low-contrast shapes fading into the packed stands, yet it perfectly retains the brightly kitted goalkeeper, holding the bounding box steady frame after frame, tracking their movement entirely on the CPU. It handles the sudden loss of high-frequency detail exactly as a robust, production-ready detector should, without jittering or losing the target.
Section 3. Let's move to and see how this builds into our first massive upgrade. Level up pose estimation.
Swapping out our standard detection model for the YOLO26 pose model requires almost no new code, which is the sheer beauty of this unified pipeline. The output tensor simply expands from our baseline to a shape of 1 by 300 by 57. What this means is that it takes our original 6 detection coordinates and effortlessly tacks on 17 COCO key points for every single detection. These key points are basically mapping out physical joints like elbows, knees, shoulders, and ankles. Each of those 17 key points comes packed with an X coordinate, a Y coordinate, and its own confidence score. We just parse it exactly like the basic detector, undo the letterbox padding used during inference, and immediately draw out the physical skeletons. Applied to live video feeds, the results are fantastic. Imagine football players twisting mid-air for an aerial header. Their complex body mechanics and limb positions are perfectly tracked through the jump. Or consider dynamic halftime dancers, spinning, jumping, and overlapping in extremely tight formations.
The OpenCV5 pipeline easily keeps a distinct, colored 17-point skeleton mapped and tracked flawlessly on every single performer in real time. No dropping frames, no confusing one dancer's arm for another's, all while running cleanly on a standard processor.
Section 4. Boss-level instance segmentation.
Peeling complex shapes and objects precisely out of a cluttered background sounds like it would be computationally heavy, right? But the math behind the scenes is surprisingly elegant. The segmentation model feeds us two specific outputs, 32 mask coefficients per object, which essentially dictate how much of a specific feature belongs to our target object, and a stack of 32 mask prototypes, which act kind of like base foundation layers. To generate the final, perfect mask, we just multiply the coefficients by the prototypes. In C++, this takes literally a dozen lines of code using a single small matrix multiplication, followed by a basic sigmoid function to snap the pixel values into place and form a solid shape.
The visual payout of that matrix math is undeniable. We get distinct, pixel-perfect colored masks that keep dancers completely separated from the background and each other, even as they cross directly in front of one another in complex choreography. In a tight close-up shot during a match, the mask effortlessly peels the player's boot away from a football, treating them as totally separate instances and holding a phenomenally clean edge around the curvature of the shoe. It's incredibly sharp, highly detailed, and again, we are executing all of this pixel-perfect segmentation entirely on a standard CPU. Section 5. Benchmarking and reproducing results. When we dive into the data, there is a massive and, honestly, surprising performance leap on the CPU for a standard 640-pixel input. OpenCV5's new graph engine, which you'll see labeled as engine_new in the code, absolutely crushes the classic DNN engine. We're talking 10.9 frames per second versus just 7.0 frames per second. That is roughly a third less processing time required per frame. It is a massive win for real-time edge applications, allowing for much smoother video analysis, and it's achieved just by switching your engine argument to new or auto in your initialization code. Before you start building and compiling your own solutions, keep these 3 essential migration gotchas in mind. First, remember that OpenCV's neural network class, cv.dnn.net, is not thread-safe. If you plan to run inference across multiple threads to speed things up for batch processing, you absolutely must give each thread its own separate instance of the network. Second, always verify that FFmpeg says yes in your configuration summary before committing to that long CMake build process. And third, always read your output tensors dynamically by their shape, like reading the row and column counts directly from the matrix, so your parser stays robust and doesn't crash no matter which model you decide to load. The absolute best part of all this, you don't have to guess how to put this complex pipeline together from scratch. There is a fully reproducible assets repository linked right in the source material. A single bash script named reproduce.sh regenerates every single image, visualization, and video we've discussed today using fixed inputs and the exact exported OnX models I've mentioned. You can clone the repository, run the script, and test this exact high-performance pipeline on your own machine right now. The ability to run advanced object detection, complex pose estimation, and pixel-perfect instance segmentation on a standard CPU entirely free of Python opens up a world of deployment possibilities for smart cameras, drones, and edge devices. So what will you build next with OpenCV5 in C++? Thank you so much for joining me today for this explainer. You can find the link to the original article in the description and the pinned comment below. Keep learning, and I'll catch you next time.